Thanks. So today I'll be talking about a project I've been working on to use previously existing data in my lab to train multivariate models to use in a real-time fMRI neurofeedback task. So we know that real-time fMRI neurofeedback can induce both behavior and cognition changes. And broadly, this can be done in two different ways. One way is by giving individuals feedback about overall activity in a particular brain region. So for example, Young gave individuals with depression feedback about activity in the amygdala to subsequently reduce depressive symptoms. Another way which feedback can be given is by giving individuals feedback about particular brain patterns. And this is what Shibata did when they gave individuals feedback about brain activity, brain patterns in the visual cortex to facilitate perceptual learning. So in decision neuroscience, people have used computational model-based fMRI to identify precise neural mechanisms associated with poor health outcomes. And so one example of this is that Gradden showed that individuals with depression have reduced striatal response to reward prediction error. So rtfMRI can be used as a great tool to target these precise neural mechanisms. And this is what I'm interested in using rtfMRI to do. And more specifically, my interest is in risky decision-making under social influence. So I'd like to use rtfMRI neurofeedback to guide behavior changes in both risk preference and susceptibility to social influence. And because my lab has studied neural mechanisms underlying both risk preference and susceptibility to social influence, this gives us a great opportunity to both train and test potential models to use to give individuals feedback before we actually implement them in a real-time environment, in a task. So my goal here is to create multivariate models to use in an rtfMRI neurofeedback paradigm for individual risk preference and susceptibility to social influence using previously collected data. So now I'll talk to you about the task which I propose using rtfMRI neurofeedback with, and which I'll use to train both of the models I'll talk about. So in this task, individuals are asked to choose between two gambles, one safe gamble and one risky gamble. In the gambles, you can see that the size of the piece of the pie represents the chance of winning the amount shown. And what makes a gamble relatively safe or relatively risky is the variance in outcomes. So you can see for the safe gamble, the variance between these two outcomes is relatively low, whereas for the risky gamble, the variance between these two outcomes is relatively high. And for the rest of this talk, you'll see the safe gamble with an S in the middle and the risky gamble with an R in the middle. So in this task, individuals are asked to choose between these two options after viewing the choices that two other players make. And through computational modeling of this task, we can obtain two parameters representing how individuals are making their decisions. The first parameter is risk preference, which is a nonlinear transformation to the values shown in the gambles. The larger an individual's risk preference is, the more they tend to choose this risky option. The second parameter is what we call other conferred utility, or OCU. This represents an additional utility added to the gamble chosen by both other players. The larger an individual's OCU, the more they tend to choose the option that they see both other players choose. Thus, the larger OCU represents more susceptibility to social influence. And a paper that we currently have in review shows that these two parameters are related to real-world health risk behaviors. And I propose using real-time fMRI neurofeedback to have individuals modulate particular brain patterns before making decisions in each trial of this task. And specifically, I'll have individuals modulate brain patterns associated with risk preference or brain patterns associated with susceptibility to social influence. So first I'll talk about the multivariate model which we will use to give individuals feedback about brain patterns associated with risk preference. So to train this model, I'll use trials without a social component to particularly target brain activity just associated with risky decision making. And so I'll put up this equation here, which is part of the equation I showed you earlier, and this is how we determine an individual's utility for a particular gamble. And it contains two components. The first component represents objective information about the gambles, including the probabilities and the values of the gamble. The second component represents an individual's subjective valuation of risk. And so if you remember, the way we define the riskiness of a gamble is by calculating the variance. And this variance is calculated using this objective information about the gambles. And univariate analyses tell us that we should further expect this first we look at brain activity associated with the variance of the gambles that individuals chose. And so we expect this brain activity to further vary based on an individual's subjective evaluation of risk. So we'll use this, again, this correlation between brain activity and the variance of the gambles an individual chose to try and predict their risk preference. So we'll put these beta maps paired up along with the individual's risk preference as estimated by this computational model into a support vector regression. And by leaving one subject out at a time, we can get a predicted risk preference for each subject. And so when we compare the true computational model parameter estimate for risk preference with the predicted risk preference estimate using the support vector regression, we see a significant correlation between the two. So there exists information in these beta maps about an individual's risk preference. And when we look further at where this information is, we see that it's in regions which we expect, which have been previously associated with risky decision-making and with risk preference. And so this includes bilateral insula and the dorsomedial prefrontal cortex. So now we have a multivariate model which we can use to give individuals feedback about brain activity or brain patterns associated with risk preference. So now I'll talk about the multivariate model which we'll use to give individuals feedback about susceptibility to social influence. So in this task, there's two types of social trials. One are what we call influence trials, while the other are what we call no net influence trials. In these influence trials, both other players choose the same option. So sometimes both other players choose the safe option, while other times both other players choose the risky option. In the no net influence trials, one player chooses one option, while the other player chooses the other option. Now because they're both choosing different options, the influence effectively cancels each other out, thus leaving no net influence. And so we'll subtract brain activity during these no net influence trials from brain activity in these influence trials to pull out brain activity just associated with social influence. So when we put these beta maps into the SVR along with the true susceptibility to social influence parameter as estimated by the computational model, again leaving one subject out at a time, we get predicted susceptibility to social influence for each model. And what we see here is that the true susceptibility to social influence, this OCU parameter, is significantly correlated with this susceptibility to social influence parameter as estimated by the support vector regression. Thus, again, here we see that there exists information in these beta maps about an individual's susceptibility to social influence. And when we look at where this information is contained, we see regions which are associated with the quote-unquote social brain or with social information processing. And this includes orbitofrontal cortex and occipitotemporal junction. So now what I've shown you is that we have multivariate models which we can use to give individuals feedback about brain patterns associated with risk preference and with susceptibility to social influence. And so now that we have these models, we can use them in a variety of different task designs. But what I'm proposing we do is to give two groups of individuals this exact same task, where we have them modulate particular brain patterns before each trial of the task I described earlier. The only difference between the two groups will be the brain patterns which they're asked to modulate. So we expect that the group asked to modulate brain patterns associated with risk preference will have subsequent changes in this computational model parameter, risk preference. And we expect that the second group, which is asked to modulate brain patterns associated with susceptibility to social influence, will have changes in the computational model parameter OCU, which again represents the individual's susceptibility to social influence. Okay, so what I've shown you so far is that we have these models which use an entire task course using all of the trials to predict these two parameters. But ultimately, what we want to do is to give individuals feedback on a trial-by-trial basis. So what I've done and what I have data for, but I unfortunately don't have time to show you today in my talk, is that I've trained models sort of accompanying these models, which we can use to give individuals trial-by-trial feedback. So for example, this risk preference accompanying model can predict on a trial-by-trial basis whether an individual will choose the safe or risky gamble. The susceptibility to social influence accompanying model can predict on a trial-by-trial basis whether an individual is in a influence trial or a no net influence trial. So I'd like to thank the Chu and Kinkasas labs and the LeConte lab, and I'd like to acknowledge those specifically involved in this project, including Pearl Chu, Brooks Kinkasas, Stephen LeConte, Jeffrey Soldate, and Jonathan Lisinski. And as I mentioned, I do have more data that I would love to show you, so please feel free to stop on my poster, number 276, or feel free to find me wandering around, and I'm happy to talk to you then. Thank you.
Okay, we do have time for a few questions for Mark.
I noticed on the SBM risk aversion prediction that there was a cloud of people that were the least risk averse, and there was a really high variance there. And I was wondering if you think there's something special about that left axis.
Sorry, say that last part again?
The points on the left axis. I wonder if you could comment.
Yeah, so yeah, there are a few subjects who appear to be incredibly risk averse, so they probably almost always chose the safe option. So you're basically asking what the SVR is doing to predict.
This says that those people potentially are using different networks, or there's something else going on, right? I mean, that would be one interpretation. Right.
So it's possible they're using some sort of heuristic during the task that's different from what we see for most other subjects. So I think that's definitely possible. It's probably worth trying to run this model, leaving those subjects out to see if we see anything different or something like that. Yeah. Thanks. Yeah.
Was the total expectation of reward balanced across the two types of choice, risk averse, not averse? In other words, you could get $38 but wouldn't happen very often in principle. But was the mean payoff balanced?
Yeah, so the task was actually, so the probabilities varied. So some trials, the safe option actually had the larger expected value, the larger payoff, expected payoff. In some trials, the risky option had the larger expected payoff. So this task was tuned specifically to try to get equal decisions between the two tasks, or the two options. Did that answer your question?
No.
Okay. Sorry.
The likelihood of getting the large, so there is a total likelihood of reward for both choices. So if you have an equal chance of getting the high payoff and the low payoff, you obviously should always choose the high payoff.
Well, you're choosing between the gambles, not the payoffs.
It's not making sense to me.
Okay, I'll walk you through the task again then. Let's see.
Well, if I'm the only stupid person here, maybe you shouldn't waste your time.
So essentially in this task, people choose between these two gambles, and they choose the gambles based on the total pie, right? So the outcome of the gamble. So if you choose a risky gamble, for example, it's you get one value out of it, and there's a 70% chance of winning 90 cents or a 30% chance of winning $38.
Okay, so 70 and 30.
Mm-hmm.
What about the other side?
70 and 30 again.
Okay, then you should always choose 38. It's simple.
Well, the probabilities will vary actually. So sometimes this probability will be up to 90%, or this will be up to this 90% will be, or this 90 cents, sorry, will be an even larger slice of the pie.
No, it's either 30 and 70 or it's not.
There's different trials in the task, and so the probabilities vary across the trials.
Well, what's the mean probability?
0.6, 60%.
Okay, we're not communicating.
Okay, maybe we can talk after.
I think also you could go to Mark's poster today
Yeah.
to talk more. And I think that we could do one quick question. Got about 30 seconds.
Thank you, very great talk. I have a somewhat related question, I guess. So since you said the probabilities vary, I wonder, I mean, it's kind of, participants have to do some sort of integration of the values together with the probabilities.
Mm-hmm.
And I wonder if the effect you're seeing also in relation to the SVM results could also be like an effect of complexity in a way. And if you have, I don't know, looked into this, I guess, alternative hypothesis, that it's not risky decision making per se, but some sort of complexity integration.
Yeah, that's an interesting point. I would guess not, because I think it's probably equally complex to compute sort of the underlying probabilities or the total expectation of what this would be, to multiply, for example, 0.3 or 0.4 by $19.60 and then multiply 0.7 by 18, as it would be to do sort of the math over here. But I'll think more about that and see if there's a way that I can get at that. Yeah, thanks for the comment. Thanks.
Okay, we do have to stop there. I want to thank all the speakers for this excellent symposium.